Now here's what's interesting about testing for continuity. If we determine that a function is not continuous at a given point, we can identify what type of discontinuity that function has. There's a third type of discontinuity in that we could have a vertical asymptote. We have already talked about what that looks like, however. Vertical asymptotes look like when you perform the overall limit, we're going to get positive or negative outside of that. So even though that's a type of discontinuity, here in this lesson we're going to concentrate on removables and jumps. Remember, a jump means that we have a vertical shift in the outputs of the function, but a removable means we just have a hole in the graph. So here's a hole, that's a removable discontinuity. Here's a jump, even though it's a small jump, it's still a jump. Here's another jump, a much bigger jump. So we're going to explore how we might discover what kind of discontinuity we're dealing with. Let's explore what's happening at x equal negative 1. We know it's a jump discontinuity. We know that's also happening at x equal 3. The output of the function exists at x equal negative 1. It's, I don't know, roughly whatever that is. Let's call that 3/4. You might call it 2/3 or something else, but we're just going to assign an output value to it, and let's say it's that value right there. Then let's look at the limit as x approaches negative 1 from the left of this function. So as we approach negative 1 from the left, the outputs are approaching 1. As we approach negative 1 from the right, the limit as x approaches negative 1 from the right of our function, is that value 3/4. So first of all, the overall limit as x approaches negative 1 for our function doesn't exist. That's the first thing we're going to look for. When that limit doesn't exist, that means we have a jump discontinuity. This tells us that our outputs take a jump on either side of that input value. And we can see the same thing's going to happen at x equal 3. Here's the output as we approach 3 from the left. As we approach 3 from the right, the output jumps all the way up here. Those two y values do not equal. The overall limit does not exist. So any time, let's just put this in our notes, any time the overall limit does not exist, the function will have a jump discontinuity. So let's explore what's happening here at x equal 1. This is a removable discontinuity. So let's look at our one-sided limits. The limit as x approaches 1 from the left of this function equals that 3/4 value. That's what it appears like to me. As we approach 1 from the left, the output value is what we called a while ago 3/4. Now let's look at what's happening as we approach 1 from the right on this function. And as we approach 1 from the right, our inputs are approaching that same value. So the overall limit exists as we approach 1. But we've already determined that we are discontinuous there because the output of the function at x equal 1 does not equal 3/4. We already determined that it equals 2. So once we've determined we have a discontinuity, we can identify what type of discontinuity by looking at the overall limit. If the overall limit does not exist, we have a jump discontinuity. If the overall limit does exist, we're going to have a removable discontinuity. So anytime the overall limit exists, we have a removable discontinuity. Now again, that's once we have determined we have a discontinuity to begin with. Just because your limit exists doesn't mean you have a discontinuity. If your limit exists and your output exists and they equal, you're continuous there. So you don't have to quantify or qualify the type of discontinuity. So there we go. So our limit tells us what type of discontinuity our function is going to have at any given input value. Now I'm going to give you a theorem that is tested on the BC exam. It's there, it's just tested in such a way that you're not going to have a problem with it. I'm going to talk to you about it. We're going to talk about it just a little bit, but we're not going to spend a lot of time on it. The intermediate value theorem says, suppose that we have a continuous function, and it's continuous over this entire closed interval from A up to B. The closed interval from A up to B. We're going to let W, capital W, be an output for the function. So here's W. Here's the point on this function, C, capital W. Then there exists a number C in the open interval. In other words, C cannot be an endpoint. C cannot equal A, and it cannot equal B. That's important. Such that the output of the function at C is W. So this point is somewhere on the interior of our closed interval that we started with. Verbally, a continuous function takes on every intermediate value between the function values from A up to B. If a function is continuous from A all the way up to B, then I am guaranteed that I am going to get an output everywhere on that interval up to and including our arbitrary value C. Well, that makes sense. This is kind of a duh theorem. Of course, that's what continuity means. But the intermediate value theorem doesn't say, and I have a lot of students that kind of go here with it, it doesn't say that that output will have to lie between f of A and f of B. That's clearly here. I have a counterexample to that. Clearly not the case. So don't put that in your head. But the intermediate value theorem says, even if I don't draw you a picture, if I tell you a function is continuous over a closed interval, and I tell you that the value that I am talking to you about is in between the open interval, it's inside the open interval, and I ask you, does that exist? The answer is yes, because you told me I was continuous on this interval. I know it really sounds like a duh theorem, but we do get some questions over it, some theory questions over it, and I just want to make sure that I cover it. So there's the end of this lesson. Come to class next time. We'll work some homework problems.